Solar roadways debunked. With our main source of energy, fossil fuels, being finite, it's only a matter of time before they run out, by around 2088 to be exact. It is therefore key to find an alternative. Julie and Scott Broussard attempted just this with their invention solar roadways. The idea is to make a section of road that houses solar cells to collect energy, thus paying for the cost of the panel. LEDs would paint the road lines from beneath and a heating element would defrost surfaces, preventing snow accumulation. Not only do they have functions on the road, but even sports courts would be made out of the panels. You could walk on and choose a sports configuration. Basketball? Ice hockey? Kids' playground? It's a cool concept, right? But are they all they seem? The Broussards received $2 million in donations to begin work on a prototype, which was completed in 2010, but is only shown to be lit at night. That's great, but how are we supposed to drive during the day? What's more is that they don't actually show it to be powering any sort of device. So does it produce enough excess energy to make the project worthwhile? Let's take a look at some calculations which take into account some typical system losses. With the SunPower E18 considered to be the best and most ideal solar panel, which has a peak value of 185 watts per square metre, the theoretical maximum, with the panel perpendicular to the sun, is 1000 watts per square metre, so we are considering the best situation here. Now for the losses. We will include a relatively realistic loss of 20% for the coverage, given that bolts and LEDs will be present on the surface. We have a 10% loss for cables and microinverters, for example in the copper. Then we have the glass, which is said to be around 15mm on top of the panels. If we imagine perfect glass, we'll say a loss of about 10%. Another major loss is the angle of the solar panel. It is not perpendicular to the sun. A typical loss for just a flat solar panel is around 20%. So with our 20% loss of coverage, we then end up going down to 150 watts per square metre. Then adding on the other 40% of losses takes us all the way down to 90 watts per square metre. But furthermore, the sun doesn't always shine, so based on data of a normal day, the output peak value would be around 7 hours. This gives us 630 watt-hours per square metre, which is 90 times 7. Taking into account the seasons as well, using real data, including cloud coverage, we can use a 0.6 multiplier for a theoretical maximum of 380 watt-hours per square metre per day. Now let's just pause for a moment, because we have to remember to bear in mind that we are imagining the LEDs can even be visible in daylight, and at such shallow angles. For a typical LED that would be used, we can see that the relative intensity from 1, if you're staring from right above at 0 degrees, drops by a whole order of magnitude to practically nothing when we reach over 100 degrees, or that is to say, the angle that we'll be viewing them at. Now let's imagine a 1 kilometre stretch of road, which is 8,000 metres squared. This stretch of road will harbour around 60,000 LEDs. If each LED needs 0.5 watts at least to be visible, then half a watt times 60,000 is 30 kilowatts. This is how much is consumed per kilometre for the LEDs of typical line markings. Now if we times this by 24 hours, we get a figure of 720 kilowatt hours for a day. Now back to the figure we had for how much energy we generated per day. We had 380 watt hours a day. Times this by the area of our section of road, and we get 3,000 kilowatt hours per day. Taking the 720 kilowatt hours a day used by the LEDs and putting that over 3,000 kilowatts produced by the road section gives us 24% used by the LEDs. That's almost a quarter. Remember though that the output value was the best case, so on a cloudy day you're going to be in deep trouble. Also, this is just the line markings, let alone any other signs that they'd want to use the LEDs to power. We won't even consider the heating element, given that we're not even close enough to powering the LEDs with these. Now let's take a look at the cost side of things. It's been estimated by Scott Broussard that a 12-foot by 12-foot segment will cost around $10,000, and to cover America's roads would be $56 trillion, or 4 times the country's national debt. Aside from costs and calculations, there are factors like strength and durability, where the power will be stored, how to wire remote road stretches to the grid, and how to keep the roads clean. What would happen if a towel broke, and would shards puncture tyres? There's no denying that solar roads are cool, but given the flaws and implications, the idea doesn't appear to be worth $50 trillion.